Oh, hi! I'm here to talk to you about gamma rays. Now, gamma rays are photons emitted from radioactive elements. In our group, we have Aaron, Kerwin, Nathan, and Patrick. I'm Nathan. When we're talking about gamma rays, there are a lot of letters we have to worry about. Now, we're going to try and describe some of these letters. We may not be able to describe them all fully. Gamma rays are measured by crystals made of sodium chloride. Gamma rays emitted from natural elements come in peaks. There are 3 peaks because there's 3 main natural radioactive elements. The most abundant is potassium, second thorium, and then we have uranium. Patrick, now to you.
Thank you there, chat. So today we are going to be looking at our gamma ray log, and basically what we're going to be taking a look at is our net to gross. So what we have here with the log is we have 1,000 feet that we are going to calculate our net to gross with. So what we're going to do is we're going to look at our log. We've got our clean over here. We have our 90% over here. So we've got our 5%, 90% shale, and we are going to calculate one green one, our zone that we're going to use to calculate our net to gross. So the area that we have is going to be our 30%, and I'm basically going to shade in the areas that we're going to use. And over here I've got them all laid out as 300 feet, 200 foot zone, and a 100 foot zone. So the area that I'm going to use to calculate is going to be right here. It's number 1, it's number 2, and there's number 3. So like I said, these are already measured out to 200 feet, 300, and 100. So basically what I'm going to do is I'm going to take each zone, I'm going to add it up, and I'm going to get 600 feet total. Then I'm going to divide by my total length of my zone, which is 1,000 feet. And we're going to go ahead and get 60% net to gross. And that is how you calculate net to gross. And today we're not drawing with Kerwin, are we?
What? Oh no.
What are you doing over there?
You know, I'm just drawing Oinky.
Okay, well why don't we talk about some GR reading corrections in logging class?
Oh yeah. Why don't we just do that then?
Yeah.
It's not like Oinky is not important. Sheesh.
Definitely not.
Alright. Let's talk about how GR reading is affected by hole size, mud density, and KCl mud.
Okay.
First and foremost, we're going to talk about hole size. Originally, we will expect an in-gouge hole, which will give us our proper GR log. This will show us where exactly how much shale and sandstone is. This is described by how the curve is done compared to the median line. But on a washout situation, especially if we do not know where washout is, we won't be looking forward to like wherever the GR log is changed. So we assume, like from this condition, we assume that there's less shale and there's less sandstone there. But what we do not know, this is because of the washout. That has washed out the shale and the sandstone in that formation. The next thing we're going to do is mud density. Mud density is affected by different amounts of barite, bentonite, and water within the solution. This will and those things are the ones that constitute basic drilling mud. And if we affect the amount of barite content within our drilling mud, we're going to get an inaccurate GR reading because barite has the innate ability to filter our gamma radiation, which will give us an inaccurate GR log. And last but not least, we'll go for our KCl melt. Talk about KCl melt. I forgot to add this thing. Our GR log is affected by 3 main radioactive materials: potassium, thorium, and uranium. So out of this, potassium and thorium will show us a clay shale content, but uranium is the one that's going to show us our organic rich material. This is what we want. I mean, this is the dollar sign. We're gonna get some of that.
Okay.
Alright. Now, when the KCl mud is weakened, the natural radioactive amount from the KCl mud, the potassium, will lead into a higher GR rating. This will we will make a wrong assumption that there's shale there, but actually this is just due to the potassium. And as such, this concludes the three main borehole environments that will affect our GR logs. Thank you.
Hi there, my name is Aaron, and today I'm going to be talking about the effects of volume of shale on the different types of logs that we're going to be considering today. Now the first one that we're going to consider is going to be our resistivity log, which is right over there. Now, as you can see over here, the percent volume of shale is quite high compared to the other regions on this graph. Now, when we move over to the resistivity graph along the same depth, we can see that the resistivity is relatively lower as compared to the other areas. Now, there are many reasons for this, but the one that we will be considering the most important is the presence of clay. Now, clay has a high affinity for fluids, and in this case, especially drilling fluid. Now, drilling fluid is composed mainly of brine solution, and as a result, it has a lower resistivity as compared to the existing hydrocarbons, and as a result, we can see this kind of low resistivity present right there. Now, another possible reason is basically, the presence of possible drilling fluids in these pores present in clay. Now, drilling fluid also has, a lower resistivity as compared to hydrocarbons, and that might be exhibited by this region over here. Now, the next graph that we're going to be considering is that of the caliper diameter. Now, in the case of shale, what happens is a phenomenon called washout basically occurs. Now, what washout is exactly, I will be explaining. Now, if you compare the regions of higher volume of shale as compared to the caliper diameter right over there, we can see that there is quite a difference between your caliper reading and your borehole reading or your bit size reading. Now, how is this possible, you may ask? Well, it's all due to the miracle of washout.
Wait, how is this possible?
Washout.
Oh, okay.
Yeah. That was Patrick, ladies and gentlemen. But anyway, the phenomenon of washout. Now, what happens is clay is basically composed of layers, and it's relatively fragile.
Wait a second. Layers? Where are the layers?
They're on the rock. You don't see the rock right now.
Okay, but are they like ogres? Because they have layers too, I've heard.
Moving on.
Okay.
We're going to be going on to how shale is basically a very fragile rock. Now, being fragile, what happens is, as you start drilling, some of these, shale formation is basically going to collapse, and as a result, you're going to get a bigger hole than your drill size. And this is basically, exhibited by the caliper log reading right here. Now, finally, we're going to talk about the gamma ray log and about how volume of shale plays a very important role in affecting its readings. Now, as evidence from lectures and by reading books, you can basically understand that, shale usually has a higher radioactivity reading as compared to clean sand or sandstone. Now, there are many reasons for this, but yet again, we're going to be considering the effects of clay. Now, clay, yet again, has a high affinity for fluids in general. Now, in this case, there are a lot of radioactive material present inside the Earth. These include, thorium, uranium, potassium, etc., etc. Now, sometimes what happens is fluids containing these radioactive materials often get into the pores present in clay, and as a result, it gives a higher gamma ray reading as compared to the relative regions. Now, this is evidence, especially right here, where we see a region of high volume of shale right here. But when we move over to our gamma ray log, we can see that the gamma ray value is relatively high as compared to the one that you can see right over there. So, that's one reason. Now, another possible reason is basically the presence of uranium. Now, uranium is, is soluble, and as a result, it often precipitates in the formation. Now, this kind of precipitation often causes a higher resistance than, what you would expect. Therefore, your volume of shale is very important and must always be considered, when you look at different types of graphs. And then now we will be talking about the possible applications of this, and in a real life situation by, being able to calculate your net to gross ratio and so forth. Thank you and have a great day.
Hi guys, right now I'm going to show you how to calculate your net to gross using your V-shale and your resistivity tracks. So that's the problem, and this is what we're going to use. We got our depth over here correlating from 10,400 down to 10,550. So again, this is our resistivity log using ohm meters. And so we correlated that against our V-shale, which is unitless, going from 0 to 1 or 0% to 100%. The 0 to 1 is just the fraction. So what we're going to do is we're going to use our Clavier corrected to end up finding out what zones here we're going to use and to perforate our formation and get the oil out that we're looking for. So this green line coming down here is our 30% line. And our 30% is going to be dropping down, cutting some of these peaks and covering some of these troughs that we're actually interested in. So if you come over here, I'll show you basically our net to gross is going to be the sum of our zone depths over the total formation depths. So what that means is over here you can see these troughs that I mentioned before, and this trough underneath the 30% line is the shale zone that is the lowest, indicating the clean zone, which is most optimal for basically housing hydrocarbons. So these top zones, or any part of the peak that is over that 30%, indicates a high zone or a high shale zone, which is not attractive in conventional reservoirs for harvesting hydrocarbons from. So basically, if you look very closely, right here we have one zone that this arrow is indicating that lies underneath this curve between these two lines that is housing some hydrocarbons that we're going to look at. And then onward we have 1, 2, 3, 4, which is this area under here, 5, 6, 7, there's that little tiny peak right there, 8 zones total. Now the reason that there aren't any zones here is because the resistivity drops down too low for us to consider it being hydrocarbon rich zones. And so basically what we do is we take all of our area under the curve, under that 30%, and we put it in our formula here after we sum all of the lengths up, and we get 62 feet. 62 feet is going to be over the total formation depth from 10,550 to 10,400. So basically you take the difference of that with under 62 feet, and you get a fraction of 0.41, or what would be 41% net to gross.
And that was the end of our presentation. Thank you for taking your time listening to us, and we're signing up.